we looked at this. So I cannot use my pointer this way. Okay, so let's look at this way. All right. So energy diagram for any chemical reaction where substrate is converted to products and to a product. And we said that if you make a plot like this, the reaction will occur spontaneously if the free energy of the product is lower than the substrate, right? As shown in this diagram. This reaction will occur spontaneously, so will occur. How fast it would occur depends how high the energy of this transition state is. The substrate, in order to be converted into product, has to go over the hump, over the hill, and the taller, the higher the hill, the harder it is to go through it. So we also said that in the presence of an enzyme, if you have an enzyme that will catalyze this chemical reaction, what enzyme will do, it will lower the energy of the transition state or will lower the activation energy. What is the definition of activation energy? The difference between transition state, the energy of the transition state, and energy of the substrate, as shown here by those red arrows. Those are the activation energy, and I think it is absolutely clear from this diagram that the activation energy, or delta G, the double decker, activation energy is lower in the presence of enzyme when you catalyze this reaction. So what does this mean? For substrate, it will be much easier to be converted into product. It has to go through much smaller hill. Okay, so reaction will proceed much faster. Now, if this diagram looked different, so if the energy of the product was higher than energy of the substrate. Right now you see this, if it was like this, product higher, would this energy occur would this reaction occur spontaneously? No. What if you added an enzyme? Would it then? No, because like we said, enzymes do not change thermodynamics. If the energy of the substrate is here, product is here, it will remain even in the presence of an enzyme like this. Enzymes only speed up the reactions that would occur anyway. Okay, so like shown here. So this is thermodynamics, but today we will actually talk about kinetics. So how fast those reactions, enzyme catalyzed reactions would occur. And in other words, so the science of enzyme kinetics is the study of the rates of those reactions. So what is the rate of the reaction where substrate A, let's call it A here, is converted into product P? So if you think about the rate, right, V, we will use the term V for velocity, V equals the first derivative over time, negative change in the concentration of A, and this is the same as change with a positive sign of the concentration of the product over time. So in other words, we're asking how fast is product showing up, or how fast is substrate A disappearing, right? This is why it is negative, because A is disappearing from your solution. And it turns out that the rate of this reaction is directly proportional to the concentration of the substrate. So I can also write that velocity equals K, constant, times concentration of A. The more substrate you have, A, the faster that the reaction will go. So K is a constant, is a rate constant, and for this simple reaction, the units of K are per second. So how fast? Per second. In also the simple case, we say that this reaction is a first order reaction. So what is the definition of the first order reaction? The rate V is directly proportional to the reactant concentration, A. You have linear equation V equals K times concentration of A. So this is a linear, direct proportion, linear reaction. So this is first order reaction. Okay, now, of course, the majority of reactions that take place in nature are not that simple, and they could be second order reactions. So you could have two substrates, A and B, giving you product P. So maybe they are combined and give you joined together, and you have product P. Or maybe two identical molecules A are coming together and are converted into product. In either way, this is a second order reaction, because if you write a V velocity, I would write again a rate constant K, but now I have two molecules, two substrates that react with each other, A and A, so A squared, or concentration of A times concentration of B. So the rate, the units for the rate constant are per second per molar to give you the correct units for V. I should be torturing you about units, but I will not. So let's just recognize second order reaction, that velocity is proportional to two concentrations, right? So you have to think about two reactants that use a substrate. Okay, now special case when one of the molecules, one of the substrates is so high, concentration is so high that it really doesn't change much when the reaction progresses. For example, water. If one of the molecules, B, was water, right? Water can participate in reaction, but water is concentration of water in aqueous solutions is so high, 55.5, that even if you are using water, this would barely change this concentration. So we could consider then concentration of water constant, and then reaction of velocity will really depend on the concentration of that second substrate. So we say it will be like a pseudo first order. So technically it is second order, but it is like, in fact, depends only on the concentration of that other substrate that is not water. Yeah, okay. Now, I should have sometimes I had some, I don't think I have today, some sound, because it should be like drums, to wake you up, if you to call your attention. This is something important coming. Henderson-Hasselbalch equation, this was so far the most important today, is at least as important as Henderson-Hasselbalch. So Michaelis-Menten, two guys, one was female, one male, like 19th century. I don't remember. I think Menten was female, but I don't remember. Anyway, I think some chemists, biochemists who first, thought about this in terms of, quantitative description of enzymatic reactions. So this is what they saw. So if I have a substrate that is converted to product, so the simplest case, one substrate, one product, with the help of E, enzyme, what will happen first is that substrate will form a complex with enzyme. Remember last time we were talking about that enzyme substrate complex. So I will form that complex, and this is technically a reversible reaction. So I can write two rate constants, K1 that goes from left to right. This is this rate constant describes you how fast that complex will be formed, and the reverse reaction, because maybe that enzyme substrate complex will actually fall apart and you will still have free enzyme and free substrate. So rate of the reverse reaction, let's call it K minus 1. Now, enzyme substrate may decide, okay, I will make a product, I will release a product. So you have what is dissociating from enzyme is not a substrate, but product. So we went through transition state and you have a product. And this rate, forward rate, is K2, and again, the backward reaction, the reverse reaction would be with K, let's designate it K minus 2. Okay, now let's start plotting our stuff. So I make a plot where I look at the amount of product on the y-axis that is formed over time. And this is your red line, so red curve. So you will see more initially. Initially we are starting from 0. Initially there was no product. You are waiting, you are measuring product, measuring product, measuring product, measuring product. Look that this is not a straight line, it saturates. It goes first, up, but then it becomes more flat, it saturates. Why? Because the longer you wait, the more product you have. It is like back pressure, okay? That product is preventing the enzyme from doing its job. So actually, at the very beginning, the velocity will be which is first derivative of product over time. We said it will be the highest. So this indeed is a very important term that we call initial velocity. So if you literally go to the lab, if you acquire this data, you can always calculate what was my initial velocity. And look, that initial velocity is always larger, higher than any velocity you would have later on. So without product at all. Okay, so Michaelis and Menten, looked at their model and they thought, okay, if we think about initial velocity, I can ignore that reverse, that K minus 2, that reverse reaction, that enzyme end product form back enzyme substrate, because initially there was no P. So at the time 0, there is really no P, so there is no reverse reaction for the second half. So you are dealing with 3 rate constants, and so this implies that enzyme combines with the substrate to form enzyme substrate, and enzyme substrate this is formed with constant K1, and enzyme substrate has 2 choices. There are 2 possibilities. Can either dissociate back into enzyme substrate, and the rate constant is K minus 1, or can produce product, and the rate constant for this is K2. Without going into skipping several pages in textbooks that show you with those assumptions, there is really a formalism and absolutely, real math behind it. You can come to the following equation. We are obviously skipping how to derive this equation, but believe me, this is the equation they got. It's valid. It was valid 150 years ago. It's valid today. The assumption to get this, exactly the only assumptions are those. So if you take this, if you start writing, what is the change, what is velocity, V0, and so on, you will get this equation, and this is Michaelis-Menten equation. So this is that equation that I say for biochemists is at least equally important as Henderson-Hasselbalch. So this relates initial velocity to, and now substrate concentration, okay? I have substrate concentration, but I have 2 constants, 2 parameters. Vmax, that is maximal velocity, and Km, that is a Michaelis constant. You have to remember this equation for sure, but we will be playing now and changing this, this equation to a little bit more useful form sometimes. But first, let's look how the relation between substrate and initial velocity would look like, okay? So this is reaction velocity or initial velocity, substrate concentration. If you really make a plot of that, function on the previous slide, you would get something like this. So this is a relation. This is how that relation looks like. Okay, so once again, your Michaelis-Menten, and this is how the curve looks like. So what is the meaning of Km? And Vmax as well, but Vmax, by the way, is more, I think, this is clear. I think you can use your intuition, and Vmax, as the name suggests, maximal velocity. So on my plot, let's maybe first talk about Vmax. This is where Vmax is, and your curve is trying to reach maximal velocity. It will never reach exactly it, but it will be approaching and approaching and approaching, right? But this is a maximal that you can achieve for this enzyme catalyzer reaction. Km is a little bit harder to see, but let's just think what happens when the substrate concentration is equal to Km at this numerator, denominator, right? So this is denominator of this. So Km plus S, we are adding Km to concentration, which means that Km units of Km is concentration. This is like a concentration. What kind of concentration? If my substrate concentration is equal to Km, I have Km plus Km at the bottom. At the top, I have Vmax times Km, because I just said substrate is equal Km. You are canceling, you are simplifying Km, and what you get is that V0, initial velocity, would equal to Vmax over 2. So 1/2 of Vmax. Because again, this will be Km. Here at the bottom, you will have 2 Kms. So after you cancel Km, you will have Vmax over 2. So in other words, Km is equal to the substrate concentration at which the reaction rate is half maximal. V0 will be, when substrate is Km, V0 equals Vmax, half of Vmax, so Vmax divided by 2. So it is half maximal. And from this plot, you can clearly, show and find Km, and indeed, V0 would be Vmax too. Or you could say, if my Vmax is that much, half of the Vmax will be here. So I am asking what my Km is, and I'm drawing those dashed lines, and I'm hitting here the point on the x-axis, which defines your Km. This is, in fact, how this Km is not coming from nowhere. It is actually related to those rate constants that we introduced earlier. But Km is a very important feature for biochemists because it is unique for each enzyme. So whatever enzyme you think about, some enzymes have this Km, some enzymes have this Km. So different enzymes have different Kms. Km is also independent of enzyme concentration. So it doesn't matter if you have very little of enzyme or a lot of the enzyme. Km would not change. Km is just a feature of the enzyme. Your Vmax would change if you add more enzyme, because you can now can produce product much faster, but Km does not change with enzyme concentration, and this really describes the properties of the enzyme-substrate interaction. Now guys, very important. Km is a measure of affinity of enzyme for substrate. The lower the value of Km, the tighter the substrate binds. The higher the value of Km, the weaker the substrate binding is. And this may look to you like, what? Okay, so let's look at an example. If you catalyze the reaction that is using the same, if you are dealing with a reaction that is using substrate A and converting it into product, but you have 3 different enzymes that use the same substrate, so we can plot them on one graph. Enzyme A, B, and C, and this is the reaction velocity versus substrate. Which has the lowest? Now let's ask question, very simple question. Which has the lowest Km value? A, B, or C? Lowest Km. A. A has the lowest because look, this I would have Vmax somewhere here. You have to take half of it, which will be somewhere there, and you are asking at which substrate concentration you will achieve it. Of course A, because you need tiny concentration somewhere here, and you are already reaching half maximal velocity. For B, I would say if this is our Vmax, we would be somewhere here, so this would be around my Km. For C, I would have to continue, probably my half maximal velocity is somewhere here. So we didn't even draw C that long, but this is where Km would be. So obviously, the lowest Km is for A. How about this? So they have different Vmaxes, but what you don't care about, that C somehow has much lower Vmax than A and B. The question is about Km. Actually, the question is phrased, which enzyme binds the substrates most tightly. So it's one step harder. We are not asking about Km directly, but the binding. So, but you have to ask yourself about Km first. So which has the lowest Km here? Lowest Km. Which saturates the fastest? C. Yeah, don't be fooled by the fact that the maximum velocity is lower. This saturates the fastest. So Km is the lowest. We said the lower the Km, the tighter the binding. Okay, the lower the value of Km, the tighter the binding. So the answer here will be C. Which enzyme binds the substrates most tightly? C. If you have, and probably you have, issues with relating Km to that strong, tight, or weak binding, what does it mean, low Km? Okay, maybe it is, let's look at this one first. It means that you need at a very low substrate concentration, you will achieve pretty high velocity. For at Km, you will achieve half maximal. And if you are somewhere here or somewhere here, we are already operating at almost maximal velocity at the saturation, at a very low substrate concentration. So what does it mean? Very little substrate is needed to completely, fully take advantage of the enzyme. Enzyme is doing perfectly its job at very low substrate concentrations here. So it means enzyme binds the substrate very tightly. That complex, enzyme substrate complex, is formed very efficiently for A, and for C not so efficiently. You have to achieve that saturation, I would have to go to the next room, or maybe even next room, okay? Because this is how slow that curve is going. To achieve maximal velocity, as I'm saying, I would have to use very, very high concentration of the substrate. Okay, now this is still the plot of the V0 versus substrate. And so here we are not highlighting Km, but we are highlighting two other features. So what happens when actually substrate is very, very low or substrate is very, very high? So if substrate is very, very low, and by very, very low, I mean much, much lower than Km. So somewhere here. Practically, again, here, so when the substrate is much, much lower than Km, much lower, your denominator will be practically Km, because this will be a small correction to Km. Substrate is so much lower than Km. So my equation will be V0 equals Vmax over Km times substrate concentration. So this is a linear relationship between V0 and substrate, which means first order reaction with respect to substrate. On the other hand, when your substrate is incredibly high, you can forget about Km, because the Km becomes a very, very small correction to the actual substrate concentration. Substrate, let's say, is 10,000 or 1,000 times greater than Km. You can ignore Km, and then you can simplify, you can cancel substrate concentration at the top and bottom, and approximately your V0 will be Vmax. Yeah, so we are approaching Vmax. We never reach Vmax, but we almost are there. So a reaction is like zero order with respect to substrate, which means it's independent of substrate. We are operating at the really saturation. Fun fact, in physiological systems, in real cells, if you think about enzyme catalyzed reactions, it just happens that the physiological substrate concentration showed by this pink box are usually below Km. So if you think about substrate being converted to a product by an enzyme, and this enzyme has Km value shown here, physiological substrates in cells would be below Km. And that is very good for us, or very, advantageous, because enzymes can, with the V0, can respond very quickly to changes in the substrate concentration. If your substrate changes, V0 will change, because we are operating in this, most sensitive region of our relationship. Now, if substrates, physiological substrates were here, much, much greater than Km, enzyme will be saturated, so it would not sense, it would not feel small changes in substrate concentration if physiologically, if this pink box was placed somewhere there. Fortunately, it is usually below Km. What are those Kms, you may ask? Anything. There are no rules, and depending on the enzymes, again, just 5 random enzymes, and Km values, again, those are units are concentration, micromolar here. You are going from very low to pretty high. So 5 millimolar, 5,000 micromolar, which is 5 millimolar, 8 millimolar, 6. Sometimes it is even below 1 micromolar. So again, it doesn't matter. KMs are all over the place, and everything depends on the enzyme. But once you say, okay, I care about chymotrypsin only, you can tell, you can tell for sure that if you use this particular substrate for chymotrypsin, Km value is 5,000 micromole. Okay, this is not practical. Even if you, are you still with me? Are you, what class is it? Remind me?
Biochemistry.
Biology number what? 450? Are we in biology 450? Okay, so what class is it? General Biochemistry 521. Biochemistry 521. I hope you're at the right place. Okay, too late. Okay, so Michaelis-Menten equation is not useful to deal with. It is difficult to draw the hyperbolic, relationship approaching K. It's difficult to determine Km. So let's alter this equation. So let's flip it over. So real equation is V0, V max times substrate, Km over Km plus S. So let's do 1 over V0. So I am flipping the rest of the equation, the right side of the equation, and this is what you will get. If you, again, I encourage you to do that simple, flipping, and you should arrive in, oh, I have it for you. Okay, so Vmax, this is our original 1 over, so I am taking this down, this goes to the top, and now this is plus, so I can say I have two terms, Km over Vmax times substrate, plus second term will be substrate, substrate over Vmax times substrate concentration. Again, you can simplify S. So you would have the final equation 1 over V0 equals a term that is Km over Vmax times 1 over S plus 1 over Vmax. And you may say, yeah, I hate it even more than I hated original one. Well, hold it, because we have now linear relationship. If this is y, and if 1 over s is your x, you have a straight line between 1 over v0 versus 1 over vs. And this representation is called Line-Weaver-Burk plot that looks like this. It's a straight line, and you don't need to have those, curves, original Michaelis-Menten. So again, on the x-axis, look that I'm plotting 1 over s, 1 over substrate concentration, this is my x, and 1 over v0 is my y, okay? Now, slope of this straight line is Km over Vmax. This is my slope. And here is the interception with the x-axis. So when y is 0, you are right there, and that intercepts. Again, you can solve it and ask at which x y is equal 0, and this is what you will get. Negative 1 over Km. That is incredibly useful. And by the way, interception with the y-axis, another thing important, is 1 over Vmax. How do I know it? Well, if my x is 0, so this term disappears because my x is 0, and 1 over V0 is 1 over Vmax. So this intercept gives you 1 over Vmax. Now, for those of you who worry about the negative values here, and if you go to the lab, if you measure, if you take substrate, particular substrate concentration, you measure velocity. You double the substrate, you measure new velocity, and so on. Of course, that velocity and substrate concentration will have only positive numbers, so those points are probably, could be real points measured in the lab. So look that we are operating only with positive numbers, but then you take a ruler or you fit a straight line, you extrapolate this to get this intercept, and you of course have intercept with y-axis where x is 0. Two enzymes, A and B, utilize the same substrate. So like we had those three enzymes before, A, B, and C. But right now, we are showing Lineweaver-Burke representations for A and for B. The lines below represent those plots, and based on these plots, you can conclude that enzyme A and B, this will be incredibly important on Friday when we talk about inhibitors, but this is an intro to inhibitors. Enzymes A and B have the same Km and the same Vmax. Enzymes A and B have the same Km, but different Vmax. They have different Km and same Vmax, or both Km and Vmax are different. Okay? So, they do intercept at the same place on the x-axis, right? And x, that intercept is 1 over Vmax. So they must have the same Vmax because they go through the same point on the x-axis. Now intercept on y is negative 1 over Km, and they obviously have intercept y-axis at two different values, right? So Km would be different. So the answer would be C. They have different Km values and the same Vmax. Should I go much faster? Do they teach you now, this, I don't know, second grade, kindergarten? We are wasting time. Maybe, but I think okay, I should phrase it this way. For some of you, it may be completely what we are talking about, linear equation. Everybody knows about the slope and intercept values for linear reactions. But from my past experience, that is not completely clear for everybody. So I encourage you, think about this. You will see questions on the quiz today, tomorrow, related to this. Or you may see a question like this on the quiz on the exam. Again, no calculators, and if you complain, I know you complain about calculators, but I use very simple numbers that I really think that a college student should be able to do this in their head. So I'm showing you one Lineweaver-Burke plot, 1 over V0, 1 over substrate, and I'm telling you what the values of those intercepts are, interception points are. So I am asking you, what is Km and what is Vmax? So you have to know that this is 1 over Vmax. So 1 over 0.01, 1 divided by 0.01 is 10. So Vmax, I have two choices, this, B, or this, or D. So now this one is negative, and because we are dealing with negative numbers, those interception points will be always negative. So this is why that negative will eventually disappear. So 1 over 0.01, which is how much? 100. So D. I really hope that you can do simple calculations like this. I would not say Km is, the intercept is negative 0.456, and calculate in your head. Of course not. But something that I say, so 1s, 0.1, 10 are valid numbers. 2 and 5s I consider also valid numbers. Because 1 divided by 0.5 is 2. 1 divided by 2 is 0.5. So I think this can be calculated in your head. Yeah. What do you think? Don't tell him.
I'm guessing C, the same numbers as on the graph.
You are guessing C. Why are you guessing C?
It's the same numbers as you have on the graph.
Because what? What? No, I really cannot hear you. What?
Because it's the same number as you have on the graph.
Yeah, but who says you have to take those numbers from the graph? You have to do something with them, like Vmax. Again, look, Vmax, this intercept, this gives you 1 over, this intercept is equal 1 over Vmax. So if you want to calculate Vmax, you have to look at this number that you have, and you have to take 1 over it, right, to get Vmax. So you cannot just take this number, yeah, and by the way, do I have it? Yeah, I have C that, like he said, are directly taken, well, not directly because this was negative, and Km cannot be negative, they always are positive, but yeah, to fool you, you know, yeah, this looks very reminiscent of this number, and this is exactly the number from the graph. Don't do it! Don't take those numbers from the graph. Work on them. Okay, so you have to remember this one is 1 over this number, gives me Vmax, and I take negative, so of this number, so will be positive, and also 1 over it to get Km. So in this case, D, the answer is D. Okay, another turnover. What is the turnover? Again, sometimes, you know, when people characterize enzymes, biochemists characterize enzymes, 2 parameters that are important are, and they are not dependent on the enzyme concentration, is Km, like we said, Michael is constant, but another one is turnover number. So turnover number tells you what is the fastest rate enzyme can go? How many molecules of substrate can it convert for product? So if we are talking about maximal maximal velocity, so the Vmax equals K2 times total enzyme concentration. So if you again think about those assumptions that Michaelis and Mentor had, if your enzyme is completely bound to substrate, so you do not have free enzyme. Enzyme substrate complex is equal to the total amount of enzyme that you have in a test tube or cell. So all enzyme is completely saturated. This is where you achieve Vmax. And then I can write the equation for this formation of the product the way it is written here. Rate constant is K2. So indeed, K2 is the rate constant that is sometimes called K-cat, catalytical, K2, K-cat, we say K-cat. Which is the turnover number, and this tells you what is the fastest rate enzyme can operate. Again, from this equation, K2 equals Vmax divided by total number of concentration. What does it mean? And I know that I'm using a lot of words, but to give you an example. You could say, if you say, turnover number is 10,000. It means that per second an enzyme can convert maximally 10,000 substrate molecules into products. Again, turnover number per second, again, varies very dramatically by orders of magnitude for different enzymes. Again, fun fact, turnover number does not necessarily, is not related to Km at all. So you could have an enzyme with a very low Km that very tightly, very readily forms a complex with a substrate, so Km is low, but its turnover number could be lousy, could be not very high. And the other way around, you could have an enzyme that has very high Km and can have low or high turnover numbers. So those are not necessarily related to each other. I find it useful, I find Km more useful than turnover, really. Again, now, not again. Reactions with very quickly, with multiple substrates. So who said that one substrate is converted into one product? You could have two substrates converted to two products. And here, if we wanted to start writing equations, well, we would need another semester because it is obviously very complicated. So we are not talking about equations, but it is good to realize, certain facts, how this reaction will progress. So you could have either sequential reactions or so-called double displacement. What does it mean, sequential? That enzyme, imagine an enzyme that is called pyruvate dehydrogenase, and it has two substrates, pyruvate and ADH. In this sequential case, two substrates have to first bind to the enzyme, and then the two products are released, lactate and NAD+. This is a fermentation, lactic fermentation reaction. This is sequential. Now, sequential could be ordered or random. So some enzyme would say, no, I need first enzyme, I need first substrate, then I bind another substrate, and I'm releasing first product. There you go, your second product. For some enzymes, it doesn't matter. Give me a substrate, one or two. I need both of them eventually, but I don't care which one will bind first. And I am spitting out the product in a random way. So again, it depends on the situation on the enzyme. Sometimes it is useful to know, what the mechanism is. And the double displacement is called sometimes ping-pong reaction. So it's shown here, substrate product. And then you are releasing a different substrate at a different product. So instead of binding substrates first, the enzyme wants, give me one substrate, give me one product, and I will present you different substrate and different product. And we will stop here because this is fancy and complicated, allosteric reactions. So on Friday, we will move from here.